Hello, welcome to the video lecture series on digital image processing. For last two classes, we are discussing on color image processing techniques. So, for last two class, we have introduced the concept of colors and the color models. In our last class, we have discussed about the RGB color model. We have discussed about the HSI color model. Along with RGB color model, we have also discussed about CMY and CMYK color models. Then after discussing about the HSI color model, we have talked about conversion from one color model to another, and we have just told about what is the difference between pseudo color and full color image processing techniques. So, in our last class, we have said that when we talk about color image processing techniques, generally we have two categories of color image processing. One is called pseudo color image processing, or this is also known as false color, so pseudo color processing, and the other category is what is known as full color image processing. So, we have just said that this pseudo color image processing, the basic purpose of pseudo color image processing technique is to assign different colors in different intensity ranges in a black and white image. The purpose is, as we have told earlier, that given a black and white image, our human eye can simply distinguish between only around 2 dozens of black and white shades or intensity shades, whereas given a color image, we can distinguish among thousands of color shades. So, given a black and white image or an intensity image, if we go for pseudo color processing techniques, that is assign different colors to different ranges of intensity values, in that case interpretation of such an intensity image is more convenient than the interpretation of an ordinary or simple intensity level image. Now, the basic way in which the pseudo coloring technique can be used, that is, as we said, that the purpose of pseudo coloring technique is to assign different colors to different ranges of intensity values. The simplest approach in which this pseudo coloring can be done is by making use of intensity slices. So, what we can do is, we can consider an intensity image to be a 3D surface. So, as shown in this particular slide, that given an intensity image, say f x y, which is a function of x and y. So, different intensity values at different locations of x and y, if we consider them to be a 3-dimensional surface, then what we can do is, we can place planes which are parallel to the image plane, that is parallel to the x y plane. So, as shown in this particular diagram, if I place such a plane at some intensity value, say x I. So, at this intensity value, say L I, we have placed a plane which is parallel to the xy plane. Now, find that this particular plane which is parallel to xy plane, this slices the intensities into two different halves. So, once I get these two different halves, what I can do is I can assign different colors to two different sides of this particular plane. So, on this side I can assign one particular color, whereas on the other side, that is this side, I can assign another color. So, this is the basic technique of pseudo coloring, that is, you slice the intensity levels and to different slices you assign different colors. So, in our case we assume, let us assume that our image, the intensity values, the discrete intensity values in a black and white image varies from say 0 to capital L minus 1. So, I have total L number of intensity values in our image, L number of intensity values. So, when we have this L number of intensity values and we assume that an intensity value say L 0, which represents an intensity level say black, this means that the corresponding f x y at location x y where the intensity is L 0, this is equal to 0. Similarly, the L minus first intensity level, I assume that this is equal to white. That means, all the corresponding pixels f x y will have a value equal to capital L minus 1. And let us also assume that we will draw p number of planes perpendicular to the intensity axis. So, perpendicular to the intensity axis means they are parallel to the image planes, and these planes will be placed at the intensity values given by say L 1, L 2 up to say L p. So, first plane will be placed at intensity value L 1, the second plane will be placed at intensity value L 2, and this way the pth plane will be placed at intensity value L p. So, obviously, in this case p, the number of planes, has to lie from 0 to capital L minus 1, where L is the number of gray level intensities that we have. So, once we place such p number of planes which are perpendicular to the intensity axis, these p number of planes divide the intensities into p plus 1 number of intervals. So, once I divide the intensity ranges into p plus 1 number of intervals, then our color assignment approach will be that a particular location, the color to a location f x y, this color will be equal to C k, or instead of calling it f, let me call it some function say h. So, the color assigned to location x y, which is h x y, will be C k if the corresponding intensity value at that location x y, f x y, lies in the range V k, where V k is the intensity range which is defined by the planes placed at location L k and L k plus 1. So, as we said that there are p number of planes. So, these p number of planes will divide our intensity range into p plus 1 number of ranges or intervals. And we call these intervals as interval V 1, V 2 up to interval V p plus 1. So, we assign a color C k to a particular location x y. So, we write H x y will be equal to C k if the intensity value at the corresponding location, which is given by f x y, this intensity value belongs to the interval V k. Now, by using this simple concept, that is, you divide your intensity range into a number of intervals, and to a particular location in the intensity image you assign a color which is determined by in which of the intervals the intensity of the image at that particular location belong. Then what we get is a pseudo colored image. So, let us see some examples of this pseudo colored image. Here we have said that on the left hand side we have an intensity image or black and white image. If I apply pseudo coloring, if I go for pseudo coloring techniques, then the pseudo colored image is as shown on the right hand side. Similarly, the bottom one, this is an image which is an enhanced version of this, and if I apply pseudo coloring technique to this particular black and white image, then the corresponding pseudo colored image is given on the right hand side. So, here you find that interpretation in the pseudo colored image or the distinction between different intensity levels in the pseudo colored image is much more easier than the distinction in the corresponding intensity image or grayscale image. Now, this particular application will be more prominent in this particular diagram. Here again you find that on the left hand side we have an intensity image or a grayscale image, and you find that in these regions the intensity values appears to be more or less flat. That means, I cannot distinguish between different intensity levels which are present in this particular diagram. Whereas, on the right hand side, if I go for pseudo coloring, you find that these different colors which are assigned to different intensity levels in this particular black and white image, this clearly tells us that what are the different regions of different intensity values in this particular black and white image. So, another application, the other application of pseudo coloring technique is from gray to color transformation. So, here what we have shown is to different intensity intervals we have assigned different colors. Now, when you go for grayscale to color transformation, then what we have to do is, if I have an intensity image or grayscale image that corresponds to a single plane, I have to convert that to 3 different planes, that is R, G and B, red, green and blue planes, and those red, green and blue planes, when they combine together, they give you an interpretation of a color image. So, that kind of color gray to color transformation can be done by using this type of transformation functions. So, here you find that our input image f x y, this is a intensity image or grayscale image. Then what we are doing is, this grayscale image is transformed by 3 different transformations. One corresponds to the red transformation, the other one corresponds to the green transformation, and the third one corresponds to the blue transformation. This red transformation generates the red plane of this image, which is given by f r x y. The green transformation generates the f g x y or the green plane corresponding to this intensity image f x y, and the blue transformation generates f b x y, which is the blue plane corresponding to this intensity image f x y. So, when these three images, that is f r f x y, f r x y, f g x y and f b x y, the red, green and blue planes, they are combined together and displayed on a color display, what we get is a pseudo colored image. But in this case, you find that the color is not assigned to different intensity ranges, but the color is decided, the color of the entire image is decided by the corresponding transformation functions. So, the color content of the color image that we will generate, that is determined by the transformation functions that we use. Now, let us see that what are the kind of color images that we can obtain using this grayscale to color transformation. So, in this diagram, as it is shown, on the left hand side we have an intensity image or a black and white image, which is transformed into a color image. So, on the right hand side is the corresponding color image, and the color transformations that has been used are like this. Here we have used that f r x y is equal to f x y. That means, whatever is the black and white intensity image, that is simply copied to the red plane. The green plane, the f g x y is generated by 0.33 f x y. That means, the intensity value at any location in the original black and white image is divided by 3, and whatever value we get, that is copied to the corresponding location in the green plane. Similarly, f b x y, the blue plane, is generated by dividing the intensity image by multiplying the intensity image by a value 0.11 or dividing the intensity image by a value 9. So, by these transformation functions, we have generated f r, the red component, f g, the green component, and f b, the blue component. And when we combine this red component, green component and blue component, the corresponding color image which is generated is like this. Now, here you should remember one point, that this color image that is being generated, it is a pseudo colored image. Obviously, it is not a full color image, or the color of the original image is not generated in this manner. So, the only purpose is the different intensity regions will appear as different colors in our colored image. So, this coloring is again a pseudo coloring, it is not the real coloring. Now, we have another example on this pseudo coloring. Here it is a natural scene, where again on the left hand side we have the intensity image or the black and white image, and when you go for grayscale to color transformation, now the transformations are like this. Here the green component is same as the original intensity image. So, we have taken f g x y is equal to f x y, where f x y is the original intensity image. The red component is generated as 1/3 of x y, and the blue component is generated as 1/9 of x y. So, by generating the red, green and blue components, blue planes from the original f x y in this manner, and if you combine them, the corresponding pseudo colored image that we get is given on the right hand side. So, here you find that if I compare the earlier image with this, in our earlier case, the colored image was showing more of red component, because in this case f r was same as f x y, whereas green and blue were scaled down versions of f x y. Whereas, in this particular case, our pseudo colored image appears to be green, because here f x y, the green component, the green plane is same as f x y, whereas red and blue are taken as scaled down version of f x y. So, if we change the weightage of these different functions of this different red and blue, red and blue planes, the color appearance will again be different. So, a grayscale image can be converted to a pseudo colored image by this kind of conversion by applying different transformations for different red, green and blue planes. Now, many of you might have seen the X-ray security machines, like what is used in airports. Here you find that this is an X-ray image on the left hand side of a baggage which is screened by an X-ray machine. If you have looked at the screen which the security people checks, on the screen this image appears in this particular form, where you find that the background has appeared as red, the different garment bags they have appeared as blue. Of course, there are different shades, whereas there is a particular region over here which has appeared as again red. Now, again this is a pseudo coloring technique which is applied to obtain this kind of image, and the purpose is, if you have a pseudo colored image like this, you can distinguish between different objects present in this particular image. And in this particular case, normally the kind of transformation functions for red, green and blue which are used are given like this. The transformation functions are usually sinusoidal functions. So, here what you have is, you have, this is the red transformation, this is the intensity values along the horizontal axis. We have the intensity values of the grayscale image which varies from 0 to the maximum value capital L minus 1. The top curve, sinusoidal curve, it shows the red transformation, the middle one shows the green transformation and the last one shows the blue transformation. And here you find that these different sinusoidal curves, it appears to be a fully rectified sinusoidal curve, is shifted from one another by certain amount. So, as if we have given some phase shift to this different sinusoidal curves. Now, when the transformations are given like this, so if you have an intensity value say somewhere here, then the corresponding red component will be generated as this value, the corresponding green component will be generated as this value and the corresponding blue component will be generated as this value. So, this particular intensity level will be coded as a color point, as a color pixel having red component given by this much, green component given by this much and blue component given by this much. Now, what is done for this pseudo coloring purpose is that you define different bands of input intensity values and the different bands are given to different objects. For example, a band somewhere here, the band somewhere here, this is for identification of say an explosive, a band somewhere here is for identification of the garment bags and so on. So, here we find that if this is the band which is given which is used to detect the explosives, the amount of red light which is generated, the amount of red component which is generated by this particular band is the maximum one. So, an explosive will appear to be a red one, whereas for this particular one which is for the garment bags, where the red component is not as high as this. So, this will not appear as that red as an explosive. So, different band of frequencies are identified or different band of intensity values are identified are specified to identify different types of items, and by using this kind of transformation we can distinguish between different objects which are there in the baggage. So, by using this pseudo coloring techniques, we can give different intensity values to different intensity ranges, and as we have just seen that we can convert a grayscale or an intensity image to a color image, where the color image as it is a pseudo colored image, it will not really have the exact color components, but this pseudo color image gives us the advantage that we can distinguish between different objects present in the image from its color appearance. The next type of image processing techniques. So, these are the two different pseudo coloring techniques that we have discussed. The next kind of image processing techniques that we will discuss is full color image processing. And as we have said that unlike in case of pseudo color techniques, in case of full color image processing, what we will do is we will consider the actual colors present in the image. And as we have said that as there are different color models, a color image can be specified in different color models. For example, a color image can be specified in RGB color space. A color image can also be specified in HSI color space. Now, because we have these different color components of any particular color pixel, so we can have two different categories of color image processing. One category of color image processing is per color plane processing. So, in case of this, in this category, what we do is you process every individual color components of the color image, and then these different processed components that you have, you combine them together to give you the colored processed image. And the other type of processing is by using the concept of vectors. So, as we have said that every color pixel has 3 color components. So, any color can be considered as a vector. So, if it is the color is specified in RGB space, then it is a vector drawn to the point which specifies the color from the origin of the RGB color space. So, there are two kinds of processing. One is per color plane processing, in which case every plane is processed independently, and then the processed planes are combined together to give you the processed color output. And the other type of processing, the other category of processing is when all the color components are processed together, and there the colors, different colors are considered as vectors. So, obviously, the color at a particular point x y, c x y, if we are going for an RGB color space, if it is specified in RGB color space, the point x y will have 3 color components. One is the red component at location x y, the other one is green component at location x y given by g x y, other one is blue component at location x y, which is given by b x y. So, every color is represented by a vector, and the processing is done by considering these vectors. That means, all the color components are considered together for processing purpose. So, accordingly, we will have two types of color processing techniques. The first kind of processing that we will consider is what we call as color transformation. Now, you may recall from our discussion with the grayscale images or black and white images that where we have defined a number of transformations for enhancement purpose, and there we have defined the transformations as say S is equal to some transformation T of R, where R is an intensity value, intensity at a location in the input image f x y, and S is the transformed intensity value in the corresponding location of the processed image g x y, and there the transformation function was given by S is equal to T R. Now, we can extend the same idea in our color processing techniques. the extension is like this. Now, in case of intensity image, we had only one component, that is the intensity component. In case of color image, we have more than one components, that is maybe RGB component if the color is specified in RGB space, or HSI component if the color is specified in HSI space. Correspondingly, we can extend the transformation in case of color as Si is equal to some transformation function Ti of R1, R2 up to Rn for I equal to 1, 2 up to n. So, here we assume that the color, every color is specified by a 3 component vector having values R1 to Rn. Si is a color component in the processed image Gxy, okay, and Ri, every Ri is a color component in the processed image Fxy. So, Si is a color component in the processed image Gxy and Ri is a color component in the input image, in the input color image Fxy. And here n is the number of components in this color specification. And Ti, that is T1 to Tn, it is actually the set of transformations or color mapping functions that operate on Ri to produce Si. Now, if we are going for RGB color space or HSI color space, then actually the value of n is equal to 3, because in all these cases we have 3 different components. Now, first application of this intensity transformation of this color transformation that we will use is intensity modification. Now, as we can represent a color in different color models or different color spaces, so theoretically it is possible that every kind of color processing can be done in any of those color spaces or using any of those color models. However, it is possible that some processing, some kind of operation is more convenient in some color space, but it is less convenient in some other color space. However, in such cases we have to consider the cost of converting the colors from one color model to another color model. Say for example, in this particular case, you find that if I have a color image which is given in RGB color space, the different color planes of the same image, this is the red color plane, this is the green color plane and this is the blue color plane. So, this color image can have these three different color planes in the RGB model. Similarly, the same image can also be represented in HSI color space, where this leftmost image gives you the H component, this gives the saturation component and this gives the intensity component. Now, from this figure it is quite apparent, as we claimed earlier, that it is the intensity component in the HSI model which is the chromatic notion of brightness of an image. So, here you find that this actually indicates what should be the corresponding black and white image for this color image. So, as we can represent a color image in these different models, so it is possible, theoretically possible, that any kind of operation can be performed in any of these models. Now, as we said that the first application that we are thinking of, that we are talking about, is intensity modification. this intensity modification transformation is simply like this. Say g x y is equal to some constant k times f x y, where f x y is the input image, this is the input image, and g x y is the processed image. And in this particular case, if we are going for color scaling, then or intensity scaling, intensity reduction, the value of k lies between 0 and 1. Now, as we said that this operation can be done in different color planes. So, if we consider the RGB color space, then our transformation will be S I is equal to the constant, same constant k times R I for I varying from for I is equal to 1, 2 and 3, where 1 the index 1 we used to indicate the red component, index 2 is used to indicate the green component, and index 3 is used to indicate the blue component. So, this indicates that all the different color planes, the red plane, green plane and blue plane, all of them are to be scaled by the same scale factor k. Whereas, if I do the same transformation in H S I space, then as we said that the intensity information is contained only in I. So, the only transformation, the transformation that will be needed in this particular case is S 3 is equal to the constant k times R 3, whereas the other two components corresponding to hue and saturation can remain the same. So, we will have S 1 equal to R 1, that is hue of the processed image will remain same as hue of the input image. We have S 2 equal to R 2, that is saturation of the processed image will remain same as saturation of the input image. Only the intensity component will be scaled by the scale factor k. The similar such operation if we perform in CMY space, then the equivalent operation in CMY space will be given by Si is equal to the constant k times Ri plus 1 minus k, and this has to be done for all the I, that is all the planes C, M and Y planes. So, if I compare the operations that we have to do in RGB color plane, RGB space, the operation in HSI space and the operation in CMY space, you find that the operation in HSI space is the minimum of these three different spaces, because here only the intensity value is to be scaled, hue and saturation value remains unchanged. Whereas, both in RGB and CMY space, you have to scale all the three different planes. However, as we said that though the operation, the transformation takes minimum time in the HY space, transformation has minimum complexity in HY space, but we also have to consider that what is the complexity of converting from RGB to HSI or from CMY to HSI, because that conversion also has to be taken into consideration. Now, if I apply this kind of transformation, then the transformed image that we get is something like this. Here the operation has been done in the HSI space. On the left hand side we have the input image, and on the right hand side we have the intensity modified image. So, this is the image for which the intensity has been modified by a scale factor of around 0.5. So, you find that both the saturation and hue, they appear to be the same, but only the intensity value in this particular case has been changed. Okay. Of course, this equivalent operation can, as we said, can also be obtained in case of RGB plane as well as in CMY plane, but there the transformation operation will be will take more computation than the transformation operation in case of HSI plane, where we have to scale only the intensity component, keeping the other components intact. The next application of this full color image processing that we will consider is color complements. Now, to define this color complements, let us first look at a color circle. So, this is a color circle. You find that in this particular color circle, if I take the color at any point on this circle, the color which is located at the diagonally opposite location in this circle is the complement of the other color. Okay. So, as shown in this figure, that here if I take a color on this color circle, its complement is given by the color on this side, and similarly the reverse, the color on this side has a complement on the color on the other side. So, this simply says that hues which are directly opposite to one another in the color circle, they are complements of each other. Now, this color complement, as we have said, the color complement, this is analogous to the grayscale negatives. When we have talked about the grayscale or intensity image processing, we have also talked about the negative operation. This color complements is analogous to that grayscale negative operation. So, the same operation which we had used in case of grayscale image to obtain its negative, if I apply the same transformation to all the R, G and B planes of a color image represented in RGB space, then what I get is a complement of the color image, or this is true really the negative of the color image. So, those color images can be obtained by a transformation function of this form. In case of intensity image, we had a single transformation, but in case of color image, I have to apply the same transformation on all the color planes, that is I have to get it S I equal to T of R I, which is equal to L minus 1 minus R I, this should be R I for all values of I, that means here I will be from 1, 2 and 3, that is for all the color planes red, green and blue, I have to apply this same transformation. So, by applying this, I get an image like this. Here you find that on the left hand side I have a color image, and on the right hand side, by applying the same transformation on all the 3 planes, that is red, green and blue planes, I get a complement image, or you find that this is same as the photographic negative of a color image. In the same manner, this is another color image, and if I apply the same transformation to the red, green and blue components of this particular color image, then I get the corresponding negative or the complement color image as shown on the right hand side. The next application that we will consider of this full color image processing is color slicing. You find that in case of RGB image, we have said that the application of color slicing is to highlight the regions of certain intensity ranges or certain intensity region. In the same manner, the application of color slicing in case of color image is to highlight certain color ranges, and this can be applied, this is useful for identification of objects of certain color from the background, or to differentiate objects of some color from some other color. The simplest form of color slicing can be that we can assume that all the colors of interest lies within a cube of width say w, and this cube is centered at a prototypical color whose components are given by some vectors say a 1, a 2 and a 3. So, as given in this particular diagram. So, here I assume that I have this cube of width w, which and the colors of interest are contained within this cube, and the center of this cube is at a prototypical color, which is given by the color components a 1, a 2 and a 3. And the simplest type of transformation that we can apply is, we can have the transformation of this form, that S I is equal to 0.5 if say R j minus A j, this is equal to w by 2 for all values of j in 1 and 3. And I said this is equal to R I otherwise. Okay. And this computation has to be done for all values of I equal to 1, 2 and 3. So, what it means that all those colors which lies outside this cube of width w centered at location a 1, a 2, a 3, all those colors will be represented by some insignificant color, where all the red, green and blue components will attain a value of 0.5. But inside the cube I will retain the original color. So, by using this transformation, you find that from this color image, if I want to extract the regions which are near to red, then I get all those red components as extracted in this right image. And for all other points where the color is away from red, you find that they have got a gray shade. Now, for this kind of application, instead of considering all the colors of interest lying within the cube, we can also consider all the colors to be lying within a sphere centered at location a 1, a 2 and a 3. So, here it is needless to say that the vector, the center location a 1, a 2, a 3, this tells you that what is the color of interest, and the width of the cube or the radius of the sphere, whichever may be the case, tells us that what is the variation from this prototype color, that we say that those colors are also of interest. The other kind of application of this full color image processing is say correction of tones or tone correction. Now, again I can find an analog in intensity image, in the simple black and white intensity image, where we have said that an image can be low contrast, it may be an image may be dark, it may be light or bright, or it may be low contrast, depending upon the distribution of the intensity values. In the same manner, for color images, we define the tone. So, a color image may have a flat tone, it may have a light tone, or it may have a dark tone. And these tones are determined by the distribution of the intensity values of different RGB components within the image. So, let us see that how these images look like in case of a color image. So, here you find that on the left we have shown an image which is flat in nature. In the middle we have an image which is having light tone, and on the extreme right we have an image which is having dark tone. Now, the question is how we can correct the tone of this color image. Again we can apply similar type of transformations as we have done in case of intensity image for contrast enhancement. So, the kind of transformations that can be applied here is something like this. If an image is flat, the kind of transformation function that we can use for this flat image is of this form. So, here it is L minus 1, here also it is L minus 1. So, if you apply this type of transformation to all the red, green and blue components of this flat image, what we get is a corrected image. Similarly, an image which is light, whose tone is light, here also we can apply a kind of transformation. Here you find that what is needed to be done is, if this image appears to be darker, then that will be an corrected image. So, the kind of transformation that we can apply is something like this. So, here it is L minus 1, here also it is L minus 1. So, here what happens is a wide range of intensity values of the intensity values in the input image is mapped to a narrow range of intensity values in the output image. So, that gives you the tonal correction for an image which is light. Similarly, for the image which is dark, the kind of transformation that can be applied here is just reverse of this. So, the transformation that we will apply in this case will have this type of nature. So, here we have L minus 1, that is the maximum intensity value. Here also we have the L minus 1, that is maximum intensity value. So, here the kind of operation that we are doing is a narrow range of intensities in the input image is mapped to a wide range of intensities in the output image. So, by applying this type of transformations, we can even go for tonal correction of the color images. Of course, the other kind of transformation, that is histogram based processing, can also be applied for color images as well, where the histogram equalization or histogram matching kind of techniques can be applied on different planes, different color planes, red, green and blue color planes of the input color image. And of course, in such cases, in many cases it is necessary that after the processing, the processed image that you get, that need to be balanced in terms of colors. So, all these different color image processing techniques that we have discussed till now, you find that they are equivalent to point processing techniques that we have discussed in connection with our intensity images or black and white images. Now, in case of our intensity image, we have also discussed another kind of processing technique, that is the neighborhood processing technique. Similar neighborhood processing technique can also be applied in case of color images, where for processing an image, it is not only the color at a particular intensity location that we will consider, but we also consider the colors at the neighboring intensity values. So, we will talk about two such processing operations. The first one that we will consider in this category is smoothing operation. So, for this smoothing, what we have is that in the smoothed image, the color component C x y, C bar x y will be given by 1 over k summation of C x y. So, where this C x y, this is actually a vector having 3 components. In RGB space, this will be red, green and blue components, and this averaging has to be done for all x y, for all locations x y, which is in the neighborhood of point x y. Okay. So, here I can simply do this operation in a plane wise manner, where we can write that C bar x y is nothing but 1 over k into summation r x y for all x y within the neighborhood of n x y. Similarly, 1 upon k summation of g x y again for all x y within the neighborhood of n x y, and 1 over k summation of b x y, where again this summation is carried out over the same neighborhood of x y. And these vectors, the average of these vectors gives us what is called the smoothed image. So, the smoothed image in this particular case, you find that on the left hand side we have the original color image, and on the right hand side we have the smoothed image, where this smoothing is carried over a neighborhood size of 5 by 5. So, as we have done the smoothing operation, in the same manner we can also go for sharpening operation, and we have discussed in connection with our intensity images that an image can be sharpened by using second order derivative operators like Laplacian operator. So, here again if I apply the Laplacian operator on all three planes, the red plane, green plane and blue plane separately, and then combine those results, what I get is a sharpened image. So, by applying that kind of sharpening operation, a sharpened image can appear something like this. So, here on the left hand side we have shown the original image, and on the right hand side you find that the image is much more sharp than the image on the left. Now, when you come for this neighborhood operations like image smoothing or image sharpening, the type of operations that we have discussed is the per color plane operations, that is every individual color plane is operated individually, and then those processed color planes are combined to give you the colored processed image. Now, as we said, the same operation can also be done by considering the vectors. Okay. Or if I do the same operation in the H S I color plane, where we can modify only the intensity component, keeping the H and S components unchanged. In such cases, the results that you obtain in the RGB plane and the results that you obtain in case of HSI plane may be different. And I give you as an exercise to find out why this difference should come. So, with this we finish our discussion on color image processing. Now, let us see some of the questions on today's lecture. The first question is, what is meant by complement of a color? The second question is, what is the complement of red? Third question, find the transformation in HSI color space to obtain color negatives. Fourth question, what is the use of color slicing? Fifth question, a color image has light tone, what type of transformation should be used to correct the tone? Sixth question, do you expect any difference in output when image smoothing operation is carried out in RGB space and HSI space? Thank you.